Welcome to The Explainer. Today we're going to talk about something that happens every single time you use the internet, but you've probably never seen it. It's this sort of invisible traffic jam, where all the ones and zeros that make up our digital world start to blur together.
So let's kick things off with a question that seems super simple, but it's actually a massive deal in engineering, right? If data is just a bunch of on and off signals, ones and zeros, what's stopping us from just flicking that switch faster and faster and faster to get, infinite speed?
Well, the thing is, there's a huge gap between how things look on paper and how they work in the real world. In a perfect, ideal world, our digital ones and zeros look like these perfect, clean little squares. But the moment you send them through an actual wire or through the air, physics takes over. And those perfect little pulses, they get stretched out and smeared.
So, here's how we're going to tackle this. First, we're going to dig into this whole data smearing problem. Then, we'll give a name to the bad guy in this story. After that, we'll talk about the rules of the road for data, the speed limits. And then comes the really cool part, the clever solution engineers came up with. And finally, we'll look at the awesome way they can actually see if it's all working.
All right, first step, the data smearing problem. Let's really look at what happens to our nice, neat data pulses the second they leave the starting gate and hit the real world.
This quote right here from the early days of communications really nails it. This is the heart of the whole problem. The sharp edges of the signals just get mushy. Each pulse stretches out and its energy starts to spill over in time. And this isn't some small little glitch. It's a fundamental property of physics that we have to deal with.
So this smearing thing, it actually has a name, and it is the primary villain of our story today. It's called Intersymbol Interference, or ISI for short. Think of it like this. Imagine saying the words data transmission really fast without any pause. It kind of mushes together into data transmission. The end of the first word just bleeds right into the beginning of the next one. Well, ISI is the electronic version of that. The energy from a symbol that's supposed to be a 1 spills over and messes with the next symbol, which might be a 0. And that's the real problem, right? This overlap is what messes everything up. The lingering tail from one pulse adds this extra unwanted energy to the symbols next to it. And that makes it really hard for the receiver to figure out, hey, was that a 1 or was that a 0? And that's exactly how you get errors in your data.
Okay, so if this smearing is going to happen no matter what do we do? How do we fight back? And more importantly, how do we do that while being smart with our most valuable, most limited resource in all of communications, bandwidth?
Decades ago, this brilliant engineer named Harry Nyquist basically laid down the law on this. He figured out the absolute theoretical maximum speed you can send symbols through a channel before they are guaranteed to interfere with each other. He gave us the speed limit for the information superhighway.
And you know what's wild? That speed limit is surprisingly simple. It's 2 symbols per second for every 1 hertz of bandwidth you have. Now, a hertz is just a measure of the channel's capacity. So let's say your highway has a capacity of 1,000 hertz. Nyquist's law says the absolute fastest you can shove symbols down that pipe is 2,000 per second. If you try to go any faster, you are guaranteed to cause a massive data pileup. That's ISI.
So wait a minute, if the speed limit for symbols is fixed, how do we get faster Wi-Fi and 5G? Well, we get sneaky. We make each symbol carry way more information. Instead of a symbol just being a simple on and off, what if it could represent one of 64 different states? If you do that, as you can see here, each one of those unique symbols can now represent 6 bits of data. That's how we crank up our bandwidth efficiency. We're just packing way more data into every single symbol we send.
But here's the thing. Packing more bits in doesn't fix the smearing. And this is where things get really clever. Engineers had this incredible aha moment. They realized this signal doesn't have to be perfect all the time. It only has to be perfect for the tiny, microscopic instant when the receiver is actually measuring it. And that insight is the key to this brilliant solution called pulse shaping.
And this slide just shows the idea perfectly. Look at that unshaped pulse on the left. See how its energy spills all over the place, right into its neighbor's time slots? Total mess. But now, look at the shaped pulse on the right. This is where the magic happens. It's been perfectly engineered so that even though it's spread out, it has this one amazing property. It crosses the 0 line at the exact instant its neighbors are being measured. It's still there, but it's completely silent at the most important moment.
And the hero of our story, the tool that performs this incredible trick, is called the Raised-Cosine Filter. It's a special kind of filter that shapes our data pulses into that perfect form, making sure that at that one precise sampling instant, the interference from all the other symbols is exactly 0.
It is our champion in the fight against ISI.
Okay, so we've got our villain, ISI, and we've got our hero, the raised cosine filter. But if you're an engineer in a lab, how do you actually know if the hero is winning? How do you measure this stuff?
I mean, you can't just look at individual ones and zeros as they're flying by billions of times a second. You need a tool that gives you a bigger picture, statistical view of how healthy your signal is.
And that tool is the eye pattern. And honestly, it's pretty cool. What you do is take the incoming stream of data and you just overlay all the bits on top of each other on an oscilloscope screen. And the result is this shape that looks kind of like a human eye. And that one picture tells you almost everything you need to know about the quality of your signal.
So let's break down what we're looking at here. That big opening in the middle, the height of it tells you how much noise the signal can handle. The wider that opening is, the more forgiving the system is to timing mistakes, or what we call jitter. And those thick, blurry lines at the top and bottom, that's a direct measure of distortion. It's like a complete physical exam for your data, all in one shot.
So this is the goal. This is what you're hoping to see, a big, wide open eye. This is the sign of a super healthy signal. It means there's hardly any ISI, the difference between a 1 up top and a 0 on the bottom is crystal clear, and the whole system can easily make the right call every time.
This, on the other hand, is your nightmare. As ISI gets worse and worse, the pulses smear into each other so much that the eye literally closes. The difference between 1 and 0 is completely lost in that blurry mess. At this point, errors aren't just likely, they're guaranteed. Your communication link is broken. So when you boil it all down, what's the big takeaway? It's that sending data at these crazy high speeds isn't about brute force. It's this beautiful, elegant dance between physics, mathematical theory, and some really clever engineering. It's about understanding the limits and then designing solutions that work with the laws of physics, not against them.
And you know, this whole process is just one of countless invisible challenges that have been solved to make our modern digital world possible. It really makes you think, doesn't it? What other hidden forces and incredible, ingenious solutions are humming away in the background every single time we send a text or stream a video?